Hello everyone. So today we will finish our discussions about evolutionary algorithms, and today we will focus on very specific implementations of evolutionary algorithms, and we'll end up with an exemplary piece of code for that, and an exemplary task. So, what are popular evolutionary algorithms? So in general, the evolutionary algorithm, general scheme is the following. So let's repeat it again. So we start with some population of candidate solutions, and we evaluate all points. Then we repeat in a loop 3 steps. First, we generate new solutions by applying mutation and recombination to our population. Then we evaluate new candidate solutions. This is the evaluation step. And then selection step is that we select from possibly old population and new candidate solutions. We select a new population. All right. So now we will look into very specific representations, very specific mutation, very specific recombination, and then we'll have an overview of different popular evolutionary algorithms. And also, so far we discussed different mutation operators, different recombination or crossover operators, different parent selection mechanisms, different survivor selection mechanisms. And now by picking these different options, we'll build new algorithms, all right? And the most popular algorithm, and one of the first proposed, is genetic algorithm. All right. Very often people refer to evolutionary algorithms as genetic algorithms. So evolutionary folks they try to be more consistent with names, and they try to keep specific names for specific representation and so on. So when we talk about bit strings or binary vectors, so we rather think about genetic algorithms, all right? And a very simple implementation of genetic algorithm is that we take 1 point crossover. So we just pick a point in a vector and we cut it in 2 parts, and then we replace 1 part between 2 parents. Mutation is just a bit flip. So at random we select positions, and we flip a bit from 0 to 1 or from 1 to 0. Parent selection is done by fitness proportional. So we discussed these 2 options. One is that we just normalize fitness function, or we can use exponential function and normalize it. And the first implementation was using roulette wheel. And the survival selection is this generational. So new candidate they replace old parents. And by the way, I didn't mention, so all these tables are taken from Gusti-Iben's textbook. So if you want to read more about this algorithm, so please go there and check them. So here we just present an overview of this algorithm, right? And again, these are examples of such algorithms, all right? So this is, if you of course change this 1 point crossover to 2 point crossover, we still talk about genetic algorithms, right? It's just a different implementation. This is just the standard, maybe one of the first or widely used algorithms that when people say about, for instance, genetic algorithm, it probably means something like that or along these lines. Evolutionary strategies that are also very old, and some people even claim that calling them evolutionary strategies is a little bit an overstatement, in the sense that this is just a stochastic optimization procedure. However, it is also called evolutionary strategy. So the idea is that we apply these optimization techniques to real valued vectors. The recombination is discrete or something like maybe no recombination at all, right? So you can use some kind of crossover. Mutation, this is important. Mutation is Gaussian. So we add some Gaussian noise to vectors, to candidate solutions. And there are different Gaussian noises used in evolutionary strategies. So we can have the self-adaptive Gaussian, that the variance changes over time, it's smaller and smaller. Or we can have this covariance matrix adaptation. So we learn this covariance matrix over time from our population, and we just add smaller noise and so on. But in general, this is all about Gaussian. Parent selection is uniform at random. The survivor selection, it's deterministic. It's either mu comma lambda or mu plus lambda. So we can add all together and select the best ones, and so on. And speciality. So this is something special about this. It's the self-adaptation of mutation step scientists. Okay, so it's not. It's when we talk about evolutionary strategies, we rather think about adaptive covariance matrix. Okay, either this is with shared variances and no correlations, or with diagonal covariance matrix, or the full covariance matrix. However, of course, if we have high dimensional optimization problems, then estimating covariance matrix could be very problematic. One pointer for the future. So evolutionary strategies were applied to reinforcement learning, and very successfully. So please remember about it, because we'll go back to that later during our when we will talk about neuroevolution. All right, this is very, very interesting application from OpenAI. Evolutionary programming. So what do we mean by that? So first of all, we deal with real valued vectors. However, we use no recombination. We use again Gaussian perturbation. But what is different is that parent selection is deterministic. So each parent creates one offspring by applying mutation. Survival selection is this mu plus mu. So you see that we generate from one parent, we generate one new individual, and we select exactly the same number of new individuals, or we generate new population by having exactly the same size as the old one. And what is the thing that is important here is that, again, the self-adaptation so the Gaussian should be adaptive somehow. So the covariance matrix should be learned somehow. There is a subtle difference between evolutionary strategies and evolutionary programming. As far as I know, it's rather that people refer to evolutionary strategies, but it's again just a nomenclature, or what people talk. Some people will tell you that this is just stochastic optimization, right, without gradients or with approximating gradients. We'll talk about it during neuroevolution lectures. Genetic programming. This is a very specific thing, and it was for some time very, very successful. Genetic programming deals with tree structures, and recombination is about exchanging subtrees from two parents. Mutation is about randomly changing or applying some changes to a tree, right? So the one difficulty here is that Of course, we don't want to create trees that are too large or with repeating subtrees, or maybe sometimes it is nonsensical to add something. So yeah, this is a little bit more tricky, I would say. However, it had really beautiful applications. So it was used to train decision trees. It was also used to discovering physical laws by fitting the best possible model to data. So the idea here was, it was a paper published in Science. So the idea was that we have some, of course, physical laws, we have some observed data, and we want to fit, in some sense, a solution of differential equations to the data, okay, by not by avoiding formulating differential equations. And then they were creating it as a tree. So it was a very quite complex, complicated combination of different functions like sinus, cosinus, with some amplitudes, phases, and so on. So they were creating it by generating a population of trees, and then they were mutating them, recombinating them, and that's why they were discovering something like new physics laws. It was a very interesting paper and very interesting concept. And I would say that this is a very good example of applying evolutionary strategies or evolutionary algorithms, to combinatorial optimization problems. Please remember, what does it mean, combinatorial, maybe? Combinatorial means that the search space is exponential, it's discrete, and it's exponential. So by changing, it is not continuous, right? This is the first important thing. It is discrete, and the objects we deal with, so they are combinatorial in nature. It means that if, for instance, we have a graph, and if we change two nodes or we change connections, we get a new graph. But also by changing, for instance, nodes and connections, we can end up with the same graph as before, maybe, or very similar. So the search space is extremely complex. It's typically exponential in nature, so it means that we have exponentially many possible objects, and it grows very quickly. So genetic programming, it's actually very nice a case for instance, optimizing tree structures, because it is very difficult to formulate an algorithm that will deal with such complex structures as trees efficiently. So if you have any problem that requires optimizing some tree structures, I would say genetic programming is a very good approach to deal with that. Another algorithm called differential evolution. So it deals with real valued vectors, and I really like this approach. In my opinion, this is very simple yet effective, and it has quite interesting properties. So to go through operators. So recombination is just uniform crossover. So we can replace values between two objects. Mutation is something which is called differential mutation, and we can maybe quickly remind ourselves what does it mean. So it means that when we have, where is my, okay. Right, so let's say that we have a candidate solution X. We sample from our population 2 points. We calculate the difference between these 2 points, right? And then we create new point by adding this difference to our current point. All right. So this parameter, this hyperparameter A, is typically between 0 and 2. All right. So what is interesting here is this delta, this difference delta. So if we go, for instance, in 2D, right, 2D case, if we calculate, let's say that we have, I don't know, 100 points, we need to calculate and choose 2 possible pairs, and we can plot them. So there will be some points that are similar to each other, some are more distant, and we'll have a cloud of points. And we sample, in a sense, if we imagine that we calculate all possible differences. In practice, of course, we don't do that. But if we do this, so we have a cloud of possible points, a cloud of possible noises that we can add to our point. All right. Normally, if we have a Gaussian, so we sample from some Gaussian, so we take, let's say, for instance, such Gaussian, and we sample all these points that are in this Gaussian. So they are more probable, they are less probable, and these are used very rarely, right? But when we have this, and of course here it's, let's say, some Gaussian with some variance, right? So this is, of course, diagonal covariance matrix. Here's sigma 1 and sigma 2. So maybe let's be more specific. Sorry, I will make it larger. Right. Now we can, of course, use this self-adaptation. We can use some other technique to estimate it over training. However, the differential evolution, it's very nice, because once we select points, the possible values that we sample, this delta, so from this set, it will probably change over time. And why? Because we converge, we start converging. So let's say that then we'll sample something like from these possible points. And this is very nice because it contains, naturally, it contains this self-adaptation. And maybe to be also, to show you what does it mean. Let's say that we are first, our points, they start like this. We cover the search space. So this is for delta. This is for axis, okay? So they are here. Let's say that during selection, we start selecting this point, this point, this point, this point, this point, this point, all right? And now we calculate again these differences, like these green ones, these deltas, and we create new points. There will be something like this, for instance. And then again, we sample something, we pick something, the best point, and we generate something new. There will be new points, and so on, that we eventually will converge to 0. Okay, so you see that so each color, this magenta, green, red, and this bluish dark, it's how it converges to a point, okay? And this is very interesting because we have this one single formula, and these possible values of delta, they shrink if we start converging somewhere. So it is natural self-adaptation in a sense, okay? Right. All right, let's go back. So honestly, I believe that differential evolution is a really interesting concept. It is a very nice alternative to Gaussian mutation or Gaussian perturbation. So I think it's worth giving it a more thought. And now let's take a look at very simple implementation of an evolutionary algorithm. And this code is also uploaded to the web page. So if you look into the assignment number 3 about evolutionary algorithm, I suggest you to also take a look how it is organized, the code is organized, and treat it as an example, and you can build on top of that, or you can propose your own structure, doesn't matter. But what is very important to have? So what is important to have is that we have our, let's say, class of an evolutionary algorithm. And what are these elements that we need to have? So first of all, we need to have fitness function, right? So in this case, we just use objective function that is given to this class during initialization. Then we have, of course, population size, and in this case, because we use Gaussian perturbation, so we use also standard deviation. And so we have fitness function. In this case, it's just objective function. We have mutation with which is just a Gaussian with predefined fixed standard deviation. And take a look. So this is we consider here only two-dimensional problem. So we just add to given point. We just add Gaussian noise, and that's it. Then we have recombination step. In this case, we don't apply it. So this is pure mutation code, pure mutation evolutionary algorithm. And then, of course, we have selection mechanism, but survivor selection mechanism. We don't have any parental selection. If you want to add it here, you need to add new function for that, okay? So how this selection works, take a look. So we first concatenate. Please remember, this is just an example, okay, of a code. So we concatenate x and x old, right? We concatenate so x and x old. What is x? X is a new mutation. So new candidate solutions, new individuals. X old is our old population. F is fitness function. So F is for current new points, new individuals. F old is for old population. So we concatenate these vectors or matrices. Then we sort fitness functions, right? And we just pick the best points. Okay, so sorry, we just pick the best. We just sort everything and we pick. This is actually missing a little bit. Sorry. So let's look into the code. Maybe it's easier. So yeah. So this code is missing a little bit. So pardon for that. So this selection mechanism it's here. So we concatenate, we sort, right, according to fitness function. So we sort it, and then we pick. As a new population, we take the population size and we pick the best points according to the fitness function. Then one single step of the evolutionary algorithm is that we apply recombination, we apply mutation, we calculate fitness function for new points, and we select the population. Okay, so we return points. So this is generate, evaluate, and select. In this example, we picked our objective function to be just quadratic function, so it should be the optimum is in 0, 0. We picked 20 as a population size. We picked 8 generations or 8 epochs, and standard deviation to be 0.5. Why 0.5? It's just from the air, okay? So it was taken to be like that. Then so here we initialized we make an instance of our class with given objective function, population size, and standard deviation. Please remember that, right now I see there is a mistake, because here we define standard deviation, but yeah, okay, so this is, oh yeah, sorry. Here we have the standard deviation to be self-standard deviation. It's fine. It's correct, okay? So going back, here we have initialization. So we take our points from a square. We initialize these points, then we calculate fitness functions, and we proceed. So here is the loop, for loop, that goes through generations, and it saves so optimum. So the optimum is just 0, 0, so we know because we want to select it. It's just for visualization, sorry. This is the main loop for performing evolutionary step. Okay, so this is for plotting, and in the end, if we look into this plot, so we start with this, intensity of the color. We see what is the first, iteration 0, generation 0, and then initialization, then we proceed with evolutionary step, and the more intense, the further we are in the optimization. And as you see, first we initialize points that are scattered all over the place, but then by selecting strongest, fittest, we start converging. And you see that we start converging to the optimal solution, right? Around optimal solution. So, yeah, please analyze this code. And so this is the final solution again. So here we see it's a little bit larger. We see that this next generations, they start to converge to this 0.00. All right. And here I would like to show you. So this is basically, this is the let's say the practical part of this evolutionary algorithms. In my opinion, evolutionary algorithms are very, very nice because they're also very simple. So it's very easy to implement it. Believe me or not, but this code was implemented within 15 minutes. Okay, so you shouldn't have any issues to implement something like that. Okay, you can use NumPy and it's enough. You can use even smart way of dealing with matrices instead of having for loops for processing single point, but you can use for loops, whatever you like, whatever you are acquainted with. So it's up to you. But this is really not difficult, okay? And now by changing basically mutation, recombination, and selection, you now play with different approaches, okay? But at the end, I would like to show you something fun. So this is an example of applying evolutionary algorithms, and this is for learning bipedal creatures. So in general, we have a complex system that contains with many different elements that they can move. They can be larger, smaller, then they have different shapes. Here we have human-looking objects, but we can have also some other objects like creatures like dinosaurs or smaller, bigger dinosaurs and so on. And the task is to learn in some sense a brain or a controller of this system. So in other words, we want to find the best parameters of these models. And here, maybe let's go back. So they used covariance matrix adaptation. So this is a version of evolutionary strategy where when we approximate using population, we approximate the covariance matrix in the Gaussian perturbation. And here they present, and this is what I love about this presentation, they present how a different controller behaves after being trained for one or more generations. So you see that in the beginning this is pretty bad, and it requires quite some time to learn something useful. I really like these videos because they show that actually some of them they seem to be very good, but then they struggle a lot and they fail in the end. You can also, of course, because this is another beautiful part of evolutionary algorithms. So we assume that our objective function is black box or non-differentiable. We don't care, right? We just want to be able to read fitness function, and that's it. And here they change it to also optimize to be faster. Okay, oops, sorry. So you can also try to maximize, for instance, target speed. Yeah, and so you see that this is actually discovered automatically. So it is very, very nice. And it shows a great potential of evolutionary algorithms. And that's why in our group, for instance, Gusti Iban and colleagues, they work with evolutionary robotics, where they train also this such objects, but they also implement in reality these robots. So if you are interested in this kind of application, so please let me know, and I will give you the contact to Gusti or maybe some other colleagues. Here you see that actually it is trained and it is able to deal with different environments. So another interesting applications, and you see that it is, it was trained and then it can deal with very specific obstacles, let's say. So it's quite interesting, and right now there are, I would say, two different approaches to such problems. So there is reinforcement learning, of course, but there is also oh, that was unexpected. But there is also all kind of evolutionary algorithms, and as we will see, I hope that we will manage to spot it. You will see that actually reinforcement learning and evolutionary approach, they're extremely similar to each other. It's just the philosophy is a little bit different, and maybe the names are different, but in general it is almost about the same. Right, so this is a very, very interesting video, and as you can see, you can play with different issues. OpenAI also provides, but not only OpenAI, other they provide very nice libraries, packages to just play with your model, and then visualization is done by yourself. In our team, we have Revolve, also code that you can play with, and you can first learn a robot and then visualize it, how it moves and behaves and so on. All right, I think that it's maybe all right. Oh, local minima. It's also very nice to see that some of these results are very peculiar. And you have in your assignments, we try to highlight this necessity of visualizing something. And here it's very similar. So it's very important to see how it behaves, right? All right. So it's here. All right. And that's it for today. Thank you very much. I hope that you have a better feeling about how to implement evolutionary algorithms, and you now believe me that this is indeed not so difficult, and you have also some glance at possibilities of evolutionary strategies or evolutionary algorithms, evolutionary computing in general. It's I would say it's really interesting field, and it's quite fascinating. As I told you, I prefer the name of population-based methods because they have this statistical background, but it's not necessarily the same, right? Evolutionary algorithms sometimes go beyond population-based methods because population-based methods are more like statistical concepts. So people look into some convergence analysis and so on. With evolutionary algorithms, it's not necessarily the case, but they overlap, and you can use these terms interchangeably. All right. The important part is that we use a population that is passed from one iteration, one generation to the other. Okay. Thank you very much. I hope that you will enjoy also working on the assignment, and please go wild. Please try to be imaginative and implement maybe your own ideas for mutation, for recombination, and so on. All right. Also, don't be afraid to add additional step in this general scheme. Maybe there is something that you are not aware of. Maybe you have some brilliant ideas. Don't be afraid, okay, and try it. Thank you very much.